Alrighty, so this unit is projectile motion. It's relatively short. There isn't a whole lot of theory behind it. Basically, how it works is I spend a day sort of talking, giving you a general overview, which is what today is. I'm going to do sort of 3 days worth of sample problems. And we're going to do, I have about 3 or 4 labs that I normally do. It's going to be a little tricky this year with these guys being out there, so I've cut it back to 2. I've sent the equipment out to Winnipegosis, and Mandy, you're going to have to come and get it, or I'll drop it off at your house for the stuff for you guys out there. I pre-explained it to some of the kids already, so it should be good. So we're going to do at least 2, the Hot Wheels one and the coffee cup ball drop that I'm going to use the new Sammy's ball bearings for. No. No. Well, I've never done the egg drop. Oh, yeah, I think so, yeah. I don't know. Okay, so here's general overview about projectile motion. So after this, you're going to be able to draw the horizontal and vertical velocity vectors for a projectile at various paths along its points along its path, and calculate the horizontal and vertical components. And those, of course, are vector components. So earlier we discussed vector quantities, velocity, acceleration. Since only horizontal and vertical motion was considered, we did not need to know about vector addition or techniques of vector resolution. For objects projected at angles other than straight up or straight down, we do. So we're going to take, up to now, everything you've ever done in grade 9, 10, 11, science, physics, what have you, has been straight line motion, right? Flat. Now, 2-dimensional motion. A little more complicated. Surprisingly, we can come up with pretty accurate results. Yeah, ballistics. Basically, that's what we're doing, yeah. Hi. Oh, it's not there? Okay. Okay, give me a second and I'll get it to you. Sorry about that. Okay, so a projectile is any object that is projected by some means and continues in motion by its own inertia. So, Mitch, we're done, right? Nate, wrap it up. Okay, so I was just talking about this in my grade 11s this morning, how an object, of course, objects in motion stay in motion. So when balls fly through the air, when Mitch is throwing to Billy, right, the ball keeps going because objects in motion stay in motion until it hits the ground because it's out of his reach. I was waiting to see if he was paying attention. Yeah. Oh, okay. A cannonball shot from a cannon, a stone thrown in the air, a ball that rolls off the edge of the table are all projectiles. These projectiles follow curved paths that at first seem rather complicated. However, these paths are surprisingly simple when we look at the horizontal and vertical components of motion separately. If there's one key thing from the entire unit, it's that. The vertical and the horizontal components have to be treated separate. And I'm just going to play my favorite video game here. Okay, so the horizontal component of motion for a projectile is no more complex than the horizontal motion of the bowling ball rolling freely along a level bowling alley. If the retarding effect of friction can be ignored, the bowling ball moves at a constant velocity. It covers equal distances and equal intervals of time. It rolls of its own inertia. What's that? Constant velocity, right? That means the velocity doesn't change. No, but it's continually moving. Like here, the ball is rolling along the floor, right? And these distances are the same distance apart. So the velocity is constant, right? When it rolls of its own inertia with no component of force acting in its direction of motion. It rolls without accelerating. The horizontal part of a projectile's motion is just like the bowling ball's motion along the alley, figure 1. If you drop a ball here, straight down, right, the VH, the horizontal component, is simply constant 0. It doesn't move sideways, right? It just drops. Well, we're going to get to that, right? But that horizontal component remains constant. I'll explain that in a bit. Interestingly enough, the horizontal component of motion for a projectile is completely independent of the vertical component of motion. They are completely separate. Nate, watch me. I'm the teacher. I do the teaching. You do the learning. Each acts independently of the other. Their combined effects produce the variety of curved paths that projectiles follow. So I keep coming back to that. The horizontal and the vertical components are independent of each other. Should be labeled too, horizontal and vertical. Okay. The multiple flash exposure figure 2 shows equally timed successive positions for a ball rolled off a horizontal table. You guys have this picture. It's probably not near as nice as mine. Yours is photocopied. I took another one here off the internet, but you can see it here. So I've got red ball right here, right? And I've got a yellow one. I don't have a yellow pen, but the yellow one is there, right? You will notice a couple things that I'm going to point out here. Investigate the photo carefully, for there's a lot of good physics there. The curved path of the ball is best analyzed by considering the horizontal and vertical components separately. There are two important things to notice. The first is that the ball's horizontal component of motion doesn't change as the falling ball moves sideways. The ball travels the same horizontal distance in the equal times between each flash. So if we were to draw a picture, and I'm having a hard time right here, I got to make this. There, that's better. Okay, so if I were to draw lines like this, and it's really hard for me to line it up, but if you took a ruler on yours, you would see that those vertical lines would be the same distance apart. Just like here, the same distance apart. What does that tell you about the horizontal motion of the yellow ball? It's constant. It's moving to the right, to your right, at a constant speed. So that's part one. That's because there's no component of gravitational force acting horizontally. There is no force moving it sideways. Why is it moving sideways? Inertia. Because objects in motion stay in motion. So the yellow ball is continuing to move sideways at a constant speed until it hits the ground, until there's some force applied to it, because right now there is no horizontal force. Gravity only acts downward, so the only acceleration of the ball is downward. The second thing to note from the photo is that the vertical positions become farther apart with time. And they've, on my picture here and on yours, I think, they've put these white lines on there to sort of help you. Right? Let me just move it farther down here. Okay, so you'll see that the red ball right here is perfectly lined up with that yellow ball right there. As is this one and this one. The balls are both falling at the same speed at every time, right? Now that speed is speeding up. Is the red ball speeding up? Absolutely it is. You can tell the balls are getting farther apart each successive picture. Is the yellow ball speeding up as it falls down? Yup. At the same rate. What rate is that? Minus 9.8 meters per second squared. Right? So the horizontal components are the same. The vertical components are the same. Okay? The downward, it's interesting to note that the downward motion of the ball is the same as that of free fall. Mitch, time to put it away. And you're looking at it, man. Okay. You're kind of hiding it with your book there, so. Okay. The path traced by a projectile that accelerates only in the vertical direction while moving at a constant horizontal motion is called a parabola. Grade 11 pre-calc, right? Yay for parabolas. I guess I should have said repeat after me. Yay for parabolas. When air resistance can be neglected, usually for slow-moving projectiles or ones very heavy compared to the force of air resistance, the curved paths are parabolic. Now, anyone that's ever golfed knows that balls don't travel in a parabola. Cole? Right? I've seen you at the golf course. Josh? Who? Yours kind of... Yeah, perfect every time. If you stand sideways at a properly hit golf ball, you'll notice that it goes up like this, and then it usually does what? If you hit it high enough, it will fall down flat, right? That's what you're trying to do when you get close to it. It's kind of like a parabola. I always forget the name of it. I always say, I got to look that up. I always forget what it is. Sand trap? Yeah. Yeah. Nate's practicing in his backyard. Avoid the swings.
No, but it's like
yeah. Yep. Same thing. What happens here is because of air resistance, there actually is a horizontal force. Because of the speed, there is a horizontal force, and so it goes up like that, and then it sort of drops flat. But anyways, so here's a question. And normally those people that have had me here and often know that I usually pull out the clickers, so unfortunately I don't have any clickers here, but question 1, at the instant a horizontally held rifle is fired over a level range, a bullet held at the side of the rifle is released, drops to the ground. So, I got my gun. Okay, and the bullet goes out like this. Another one drops to the ground at exactly the same instant that it's fired. No. You've got a bullet on the side. Like you got your bullet in one hand and you pull the trigger, and then at the same time you pull the trigger, you drop the bullet. So one bullet goes flying out sideways. The other one just drops straight down. Okay? Which one hits the ground first? The one that's dropped, the one that's fired, same time, or it could be either one. Same time. That's what I've been talking about. Well done, Billy. Right here. There it is right there. There's the proof. It's weird, right? Like if you think a bullet or a marker, right? Like if I hold a bullet like this, that's exactly how long it takes for the bullet fired out there downrange for it to hit the ground.
Yeah, it also depends when you're firing.
Oh, absolutely. You got to be firing perfectly flat.
What if you like aim a little bit up?
Well, then it's going to go like this, right? Yes, it will. It's got to be fired perfectly flat.
At the same time, if you got that at night.
Flat. I would say that's 0 degrees. Apparently, I have a video about this. Okay, Nate, that doesn't mean you have to do it. Oh, they see the video too. It's just the quality's probably not as good. Okay, so now the question is, and Nate and Cole and a couple other people have talked about, that's assuming that that rifle is fired straight sideways. So, consider a cannonball shot at an upward angle. Pretend for a moment that there is no gravity, then according to the law of inertia, the cannonball will follow a straight line. So here it is right here, right? It's going to be fired straight up like that because there's no gravity.
Gravity's going to be like a big factor for this field, right?
Yeah. But there is gravity, so this doesn't happen. What really happens is the cannonball continually falls beneath this imaginary line until it finally strikes the ground. Get this. The vertical distance it falls beneath any point on the dashed line is the same vertical distance it would fall if it were dropped from rest and had been falling for the same amount of time. In other words, right, if it takes 3 seconds in this imaginary spot, imaginary non-gravity world to get to here, if you were to drop a cannonball from that height, it would go there, right? So this distance here is the same height that it would fall if it was dropped from rest. So in other words, it's still falling exactly the same. The horizontal speed has nothing to do with the amount of drop. It's kind of counterintuitive. People think, oh, if it's faster, it's going to take longer to hit the ground. Same time. And this distance is given by d equals 1/2 gt squared. D equals VIT plus 1/2 AT squared, where the VI is 0. Vertical. The horizontal and vertical are completely independent. We can put this another way. Shoot a projectile skyward at some angle and pretend there is no gravity. After so many seconds t, it should be at a certain point along a straight line path. But because of gravity, it isn't. Where is it? The answer is it's directly below the point. How far below? 5t squared meters, or 4.9. 1/2 gt squared. Note another thing from figure 3. The cannonball moves equal horizontal distances in equal time. This distance here, there's 1 second, 2 seconds, 3 seconds. Same distance, same speed horizontally. That's because no acceleration takes place horizontally. That is key. The only acceleration is vertically, up and down, in the direction of Earth's gravity. The vertical distance it falls below the imaginary straight line path during equal time intervals continually increases with time. Well, g is gravity, right? So the acceleration has been replaced by g. It's a constant 9.8. Figure 4 shows vectors representing both horizontal and vertical components of velocity for a projectile following a parabolic path. Notice that the horizontal component is everywhere the same, and only the vertical component changes. You will notice here, if I draw it right here, that blue one right there, that's the horizontal component. And if I take it and I move it here, and here, here, and here, it's always the same. Note that the actual velocity is represented by the vector that forms the diagonal of the rectangle formed by the vector component. So the actual velocity that you would see is this one here in red. What is the diagonal right here? Well, it's just the horizontal. How come? Because there's no vertical. Guys good out there? Yeah, okay. Okay, good. At the top of the path, the vertical component vanishes to 0. So the actual velocity there is the horizontal component of velocity at all other points. Everywhere else, the magnitude of velocity is greater, just as the diagonal of a rectangle is greater than either of its sides. Sort of. Figure 5 shows the path traced by a projectile with the same launch speed at a steeper angle. If you fire it at a steeper angle, guess what? It's going to go higher, right? Still a parabola, though. That's right, Nate. Note that the initial velocity vector has a greater vertical component than when the projection angle is less. The greater the component results in a higher path. But the horizontal component is less, so the range is less. This bottom one doesn't go as far. But it's not because you didn't shoot it very fast. It's because the horizontal component is less. It's not going as fast sideways. Does it go higher in the air? It does. So if it goes higher in the air, it actually stays in the air longer. So might it end up at the same spot? Is there a way to make it at the same spot? Is there a way to fire if I go up to here? Can I do this? Can I fire it higher in the air and land it right there? Is that possible? The same spot? There's no way? Like, I mean, can I take my marker, right, and just try to land it like 4 or 5 feet away from me? Or can I throw it way up in the air and land in the same spot? Well, of course you can. But the trick is, what are those two angles? Hey? 60 and 30? Or, like, are you saying like 20 and 70 would do the same thing? Figure 6 shows the paths of several projectiles all having the same initial speed, but different projection angles. The figures neglect the effects of air resistance, so the paths are all parabolas. Note that these projectiles reach different altitudes or heights above the ground. They also have different horizontal ranges or distances traveled horizontally. And Mitch is right. There's the 30-degree one. There's the 60-degree one. They land at the same spot. One just goes higher. The remarkable thing to note from figure 6 is the same range is obtained from two different projection angles. Angles add up to 90 degrees. An object thrown into the air at an angle of 60 degrees, for example, will have the same range as if it were thrown at the same speed at an angle of 30. For the smaller angle, of course, the object remains in the air for a shorter time. So the question is, what's the maximum range then? What angle do you have to throw something to get it to go the furthest? 45. Exactly. 45 is the magic angle. Generally, there are certain rules depending on how heavy things are and stuff, right? Because of air resistance and stuff like that. So figure 7. Maximum range is attained when the ball is batted at an angle of nearly 45 degrees. You guys have a different picture. In cases where the weight of the projectile is comparable to the applied force is when a heavy javelin is thrown. So if you've ever thrown a javelin, you know they're fairly heavy. The applied force does not produce the same speed for different projection angles, and maximum range occurs for angles quite a bit less than 45. So heavy objects like shot puts and javelins, fairly heavy things, you actually want to throw them at less than 45. We've emphasized the special case of projectile motion without air resistance. When there is air resistance, the range of projectile is somewhat shorter and is not a true parabola. So this, in fact, is the actual path, like I was talking about before about the golf ball, right? Do you think that the Army and military units know about all this stuff when they're trying to bomb things? Absolutely, right? They've got it pretty much to a pinpoint. They're using GPS, they're using other things, but originally they would have to know a lot about this kind of thing. Okay. The CSI people are going to know how bullets work and stuff like that too, right? The CSI people, like I don't mean like the guy on TV, the crime scene investigators.
Oh, yeah. Thanks a lot,
A projectile is shot at an angle into the air. If air resistance is negligible, what is its downward acceleration? Projectile is shot into an angle in the air. What is the downward acceleration? Always. AV, vertical acceleration, is always minus 9.8. No. Vertical acceleration. Vertical acceleration is always minus 9.8. No.
So physics is completely different.
And there's all that relative speed stuff, right? More or less. The gravity's slightly less, but you got bigger problems to worry about than the gravity. Theoretically, it would be, yeah. You mean the place, not the man, right? Yeah. Are you impressed that I... Yeah? Oh, yeah? I'm nuts.
They're nuts.
It's actually, I just saw something the other day in one of my nerd thing that comes on my science feed or whatever, but it showed that there's different actually regions of the planet where the gravitational field is slightly different, and they think it has something to do with the core of the Earth, the iron core and stuff. It's not. No, it's not. But I mean, you're talking like 4 or 5 decimal places down. Yeah. For our purposes, 9.8 is plenty good. No, it's not 6. What's the horizontal acceleration, Nate? What's AH? Horizontal acceleration. Yes, I have. Horizontal acceleration? 0. Objects do not accelerate horizontally.
Oh yeah, I have it written down right here.
0. But remember, Newton said objects in motion stay in motion, right, at a constant speed. The only thing that this is without air resistance. Obviously, air resistance plays a large role, right? And when the Mythbusters did their thing, they had to account for air resistance as well. Yeah, that's true, yep, where there's no atmosphere. Of course, that was all fake, though, right? Yeah, it's all faked. At what part of a path does a projectile have minimum speed? When is it going the slowest, Nick? When is it going the slowest? At the start, at the end, or at the peak? Or is it the same speed throughout? Josh, what do you think? When is it going the slowest? Cool? I'll get to that in a sec. At what part does it have minimum speed? It's right there at the peak. I saw Noah going like this. Does that mean the peak, Noah? Did you get that right? Yeah? Yeah? Or were you putting your hand up trying to answer? No? Okay, yeah, it's at the peak. Why is that? Because the horizontal component stays the same, right? And you have to add the vertical, There's no vertical here to add, right? So if this is 6 and this is 8, then the total there would be 10, right? So here it's just 6. It's only the horizontal. There's no vertical to add. So the minimum speed is actually at the peak. So how fast, without air resistance, how fast is the bullet going when it hits the ground? The same speed that it left the gun. Yep. But it's lost speed as it goes up, right? So then as it comes down, it gains speed. So it would gain as much as it lost on the way up. So when you see those guys running around on horses, there's revolution somewhere, and they're shooting guns in the air, guess how fast those bullets are coming straight back down? Same speed. You better be moving out of the way. Coming down just as fast. Can you give me about maybe 2 or 3 minutes, Nate? I'm pretty close to wrapping up here, I think. Is that right? Why didn't you go? If air resistance is small enough to be negligible, a projectile will rise to its maximum height in the same time it takes to fall from that height to the ground. This is because deceleration by gravity while going up is the same as acceleration by gravity while coming down, right? That's important there. The deceleration going up is the same as the acceleration while coming down. So the projectile rises to the ground with the same speed it had when it was projected from the ground. So the launch speed, which is quite often referred to as the muzzle velocity, it's how fast it leaves the muzzle. The muzzle velocity is the same as the landing velocity, provided that one thing, right? If you launch from ground level and you land at ground level, it's going to be the same. But what if you don't launch from ground level? What if you shoot off a cliff? Going to be going faster, right? And really, when you're standing with a rifle and you're holding it at shoulder height, you are launching it off a cliff, which would be this kind of thing, right? No? Who knows? I mean, and it depends on where it's caught too, right? Okay, if an object is projected fast enough, let's try to finish up here so Nate can go. Yeah, don't shoot an eagle. If an object is projected fast enough so that its curvature matches the curvature of the Earth and it's above the atmosphere so that air resistance doesn't affect its motion, it will fall all the way around the Earth and be an Earth satellite. This interesting topic is treated in UCM unit. We'll get to that. Okay? If this is the curvature of the Earth and you fire a gun at the same angle as the curvature of the Earth, oh, I've lost my, right? It will actually orbit. That is really bad. Yes, I hate that. I don't know. It's weird, eh? I was trying to make some smart comment, but I was thinking about silence doesn't last forever. Okay, Nate, you can go to the bathroom while we watch some cool videos. Oh. Tomorrow I will start the sample questions. You should note there on that outline that I gave you, and I'll just take a quick second to go through it. Yeah. There are only really 7 types of projectile motion problems, and some you've actually dealt with already. There's the actual outcomes, but basically it's problems, right? So you might want to jot these in on that outline. We've got a couple minutes here left. So horizontal ground straight up. So something fired straight up into the air and down. You did those in grade 11. You guys got to run? Okay. Horizontal, getting a haircut again? Or no, that was Jake who was getting his haircut again yesterday. Or nothing. Horizontal ground at an angle. So that's one that we'll deal with. Off a cliff, dropped. So from a height, like it could be, come on, go down. The first one was straight up. It's on another handout. Do you guys have it? I think you have it. The same day you got the first one. Oh, okay. You have it? Nick, you got this one? Yeah, right there. Perfect. Okay. Okay, let me see if I can get this straight again here. I'll put it on. Let's do this. Oh, it's right there. Okay, perfect. So straight up and down, horizontal angle, horizontal ground at an angle, off a cliff dropped. So just like dropped like that, right? Number 4, where's number 4? Oh, this thing. Is that what number 4 is? So number 4, I don't know where it is here on your page, but I'm going to draw here. So off a cliff, thrown straight down. So in other words, it's projected at some speed down, right? So here, the VI is 0. Here, the VI is greater than 0. You're firing it straight down, right? Because it says off from. I'm saying it, Nate. Nate, I've only got so much time. Let me get through them. I haven't got to 5 yet. Let me get there. Off a cliff, thrown up and then down. Okay, so one is thrown downward, the other is thrown upward. Right? Off a cliff, projected horizontally. That's our first lab that we're gonna do. So something that's like a car driven off a cliff, that type of thing, straight. And then the last one is the Big Daddy, off a cliff, projected at an angle. That's the one, the Mythbusters slide. Okay? We're gonna be doing that one in the lab as well. So those are the 7 types of problems you can expect. For sure, one of these, it'll be the biggest problem you've ever done. Guaranteed. For sure one of those. For sure one of these on the test. And then the other ones, probably one of these, because they're all 2-dimensional. And then there might be 1 or 2 other ones along the way. Okay? So I'm going to do 3 days worth of sample questions, and then we'll do some labs.